As we just saw, the partially positively charged carbon atom will act as electrophilic site where the nucleophile can attack, and hereby an alkoxide ion is formed. Conversely, the partially negatively charged oxygen atom constitutes the nucleophilic site and can, for example, react with a proton to form a protonated carbonyl. And in general, aldehydes and ketones react in 3 different mechanisms. The first option is a nucleophilic addition reaction, then the second is an alpha substitution reaction, and the third is a carbonyl-carbonyl condensation reaction. And all these reactions we will discuss in the following slides as well as in the next lectures. The most common reaction of aldehydes and ketones is a nucleophilic addition reaction with either a negatively charged nucleophile or a neutral nucleophile. Now we will start with an overview of the nucleophilic addition reaction with a negatively charged nucleophile. A negatively charged nucleophile can, for example, be a hydride ion or a cation or also a cyanide ion. And in the first step, the negatively charged nucleophile will attack the electrophilic site, hence the partially positively charged sp2 hybridized carbon atom. And hereby, alkoxide ion intermediate is formed. In this alkoxide ion, the carbon atom is now sp3 hybridized. And this first step, the addition of the nucleophile to the carbonyl group, is irreversible for an hydride ion or a cation. However, it is reversible for a cyanide ion. Then, in the second step, the intermediate alkoxide ion gets protonated to form the product which contains a hydroxide group. And if we have a closer look on the orbitals, we can see that the filled p orbital of the nucleophile interacts with the empty pi star orbital of the carbonyl group. And the filling of the pi star orbital causes the break of the carbon-oxygen pi bond. And the addition of a nucleophile is energetically favored, as a strong carbon nucleophile sigma bond is formed at the expense of the weaker pi bond in the carbon-oxygen double bond. And for the attack of the nucleophile, the maximum overlap of the orbitals is achieved when the nucleophile approaches here to the carbon-oxygen double bond in an angle of 90 degrees. However, the electron density of the oxygen repels the nucleophile and forces it to attack at an angle of 107 degrees instead. This angle is also called the Bürgi-Danitz angle. So the nucleophile can also be neutral, and for example, a neutral nucleophile is then water or alcohol or also a primary amine or a thiol. In this case, the nucleophile contains at least one hydrogen atom which is bonded to a heteroatom. And then, in the first step, the nucleophile attacks the carbon of the carbonyl group, and the formed intermediate contains now both a positive and a negative charge. And this nucleophilic attack is again on the sp2 hybridized carbon atom of the carbon-oxygen double bond. And then subsequently, an intermolecular proton transfer takes place, whereby the nucleophile acts as a base. Subsequently, another intramolecular proton transfer takes place, and now the protonated nucleophile acts as an acid. And hereby a proton is transferred from the nucleophile towards the oxygen atom in order to produce the product which contains a hydroxide group. Important to see is that all these 3 steps are reversible, and very often an acid catalyst is added in order to increase the rate of the addition of the neutral nucleophile to the carbon-oxygen double bond. The second type of reaction is an alpha substitution reaction, and an alpha substitution means that the reaction takes place at a carbon atom next to the carbon-oxygen double bond, so in alpha position. And hereby, a hydrogen atom which is attached to the alpha position is replaced by another group in a 2-step reaction. Usually, the alpha substitution reaction takes place under basic conditions. So in the first step, a base deprotonates the aldehyde or the ketone in alpha position. And hereby an enolate ion is formed. And this enolate ion is a strong nucleophile which reacts then in the second step with an electrophile in order to introduce a new substituent in the alpha position. And the third type of reaction is a carbonyl-carbonyl condensation reaction, which involves two carbonyl groups which react with each other. Hereby, one carbonyl group undergoes an alpha substitution reaction while the other undergoes a nucleophilic addition reaction. And for example, an aldol condensation is such a carbonyl-carbonyl condensation reaction. If we have a look on the aldol condensation of ethanol, we can see that in the first step, the proton in the alpha position of ethanol is removed by the base and an enolate ion is formed. This enolate ion reacts then in the second step with an electrophile, and the electrophile is now the second molecule of ethanol, which is not deprotonated. And hereby a new carbon-carbon bond is formed. And this molecule is also called alkoxide ion. Then in the third step, this alkoxide ion gets protonated in order to produce the aldol addition product, which contains now an alcohol group as well as an aldehyde group. And also important to see is that in the third step, the base is regenerated. That means the base acts as catalyst in this reaction. And usually the aldol condensation ends with a fourth step where the aldol addition product is heated with either a base or an acid to form a conjugated enol by the elimination of water.